Now, it was Euler who took the decisive step and said, hey, look, I'm going to call that e to the I theta. Now, why did he do that? Well, because everything seemed to indicate that it should. But that's certainly worth the best color we have, which is what? Getting low here. Okay. Nonetheless, it's worth pink. I'll even give him his due, Euler. Sometimes it's called Euler's formula, but it really shouldn't be. It's not a formula, it's a definition. So in some sense you can't argue with it. He said, well, if you want to call putting a complex number in a power and calling it that, you can, but one can certainly ask why he did it, and the answer, I guess, is that all the evidence seemed to point to the fact that it was the thing to do. Now, I think it's important to talk about that a little bit because it's, in my opinion, if you're seeing this for the first time, even if you read about it last night, it's a mysterious thing, and one needs to see it from every possible point of view. It's something you get used to. You will never see it in a sudden flash of insight. It'll just get as familiar to you as more common arithmetic and algebraic and calculus processes are. But look, what is it we demand? If you're going to call something an exponential, what is it we want an exponential to do? What gives something the right, an expression like this, the right to be called e to the I theta? The answer is I can't creep inside Euler's mind. It must have been a very big day in his life. He had a lot of big days, but when he realized that that was the thing to write down as the definition of e to the I theta. But what is it one wants of an exponential? Well, the high school answer surely is you want it to satisfy the exponential law. Now, to my shock, I realize a lot of people don't know. In my analysis class, these are some math majors or graduate engineers in various subjects, and if I say prove such and such using the exponential law, I'm sure to get at least half a dozen emails asking me, what's the exponential law? Okay, the exponential law is a to the x times a to the y equals a to the x plus y. The law of exponents. That's the most important reason why that's the single most important thing about exponents and the way one uses them. And this is the exponential function, called the exponential function, because because all the significant stuff is in the exponents. All right, so it should satisfy, we want, first of all, the exponential law to be true. But that's not all. That's a high school answer. An MIT answer would be, what is the role of, why is e to the x such a popular function? Well, of course, it does satisfy the exponential law, but for us, an even more reasonable thing, it's the function which, when you differentiate it, you get the same thing you started with. And it's, apart from a constant factor, the only such function. Now, in terms of differential equations, it means that it's the solution that e to the, let's be a little generous, make it e to the ax. No, better not to use x, because x, complex numbers tend to be called x plus iy. Let's use t as a more neutral variable, which is standing outside the fray, as it were. It satisfies the relationship that it's the solution, if you like, to the differential equation. That's a fancy way of saying it. dy dt equals a times y. Now, of course, that is not unique. We could make it unique by putting an initial value. So if I want to get this function and not a constant times it, I should make this an initial value problem and say that y of 0 should be 1. And now I will get only the function e to the at. So in other words, that characterizes this function. It's the only function in the whole world which has that property. Now, if you're going to call something e to the I theta, it should have, we want that to be true. So here are my questions. Is it true that e to the I theta 1, let's use that, times e to the I theta 2? Oh, I see I'm on a collision course here, but that's easily fixed. Is that equal to e to the I theta 1 plus theta 2? If that turns out to be so, that's a big step. What would we like to be true here? Well, will it be true that the derivative with respect to t of e to the I theta, I would like that to be equal to I times e to the I theta. So, question? Question. I think those are the two most significant things. Now, the notes do a third thing, talk about infinite series. Since we haven't done infinite series, it's not officially part of the syllabus, the kind of power series that are required, but I will put it down for the sake of completeness, as people like to say. So it should behave right with the infinite series should be nice. Infinite series should work out, should be, there is no word for this, should work out, let's say. And what's the little music? Is that some weird music I hear, or is it only me that hears it? Yes, Lord. Somebody up there, I feel I'm being watched up there. This is terrible. So there's one guy, here's another guy. And I won't put a box around the infinite series since I'm not going to say anything about it. Okay, now these things in fact are both true, otherwise why would I be saying them? And why would Euler have made the formula? But what's interesting to see is what's behind them. And that gives you a little practice also in calculating with the complex numbers. So let's look at the first one. What will it say? It is asking the question, it says, please calculate the product of these two things. Okay, I do it, I am told. I will calculate the product of cosine theta 1 plus I cosine theta 2 sine. Sine theta 1. That's e to the I theta 1, right? So that corresponds to this. The other factor times the other factor, cosine theta 2 plus I sine theta 2. Okay, what does that come out to be? Well, again, we'll use the method of grouping. What's the real part of it? The real part of it is cosine theta 1, cosine theta 2. And then there's a real part which comes from these two factors. It's going to occur with a minus sign because of the I squared, and what's left is sine theta 1, sine theta 2. And then the imaginary part, I'll factor out the I, and then what's left I won't have to keep repeating the I. So it will be sine theta 1 cosine theta 2. And the other factor will be cosine theta 1 sine theta 2 plus sine theta 2 cosine theta 1. Well, it looks like a mess, but again, high school to the rescue. What is this? The top thing is nothing in disguise, but it's a disguised form of cosine of theta 1 plus theta 2. And the bottom is sine of theta 1 plus theta 2. So the product of these two things is this, and that's exactly the formula. In other words, this formula is a way of writing those two trigonometric identities for the cosine of the sum and the sine of a sum. Instead of the two identities taking up that much space written one after the other, they take up this much space and they say exactly the same thing. Those two trigonometric identities are exactly the same as saying that e to the I theta satisfies the exponential law. Now that's, people ask, what's beautiful in mathematics? To me, that's beautiful. I think that's great. Something long turns into something short, and it's just as good, and moreover connects with all these other things in the world, differential equations, infinite series, blah, 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 blah. Okay, I don't have to sell Euler, he sells himself.